The next thing we need to kind of review, hopefully you've done it already, spend some time, go to the simulation, send a pulse down. This is the one we used in grade 11, so it's like the Slinky lab. If you got to do the lab at school, you're going to send a pulse down a string, set the damping to 0 because then we don't have to worry about friction, and see what happens to that pulse when it reflects off a fixed end, and see what happens to that pulse when it reflects off a loose end. So if you haven't looked at that simulation, go look at it now. The outcome is when a wave hits a fixed end, the phase of the reflected wave is different than the ingoing wave. So if it went in as a crest, it reflects off as a trough, as opposed to when a wave hits a loose end. Then the reflected wave has the exact same phase. If it went in as a crest, it comes out as a crest. That was a grade 11 thing that we did when we did the Slinky lab. We didn't really do anything with it in grade 11. We just wanted to set the tone and have it in your brain so when we come back to it today that this isn't totally new to you. So think back to grade 11. When a wave reflects, the reflected pulse depends on what it reflected off of. Here's how we're going to use this with wave optics. First of all, we don't see phase. Like if a beam of light hits me in the eyeball as a crest and a different beam of light at another time hits me as a trough, I wouldn't see the difference between crests and troughs. We don't see phase on its own, so this is a little bit abstract. What's going to happen though, stumbling on my words. When light reflects off a material with a larger index of refraction, so basically in this topic we're going to be talking about light bouncing off of other materials and how that light interferes. If we talk about light reflecting off a material that has a larger index of refraction, when it does that, then the phase of that light will change. As opposed to if light reflects off a material with a lower index of refraction, that's kind of like a loose end, the phase of the light will not change. So the bottom line is if light reflects off something with a larger N, you get a different outcome than if light reflects off something with a smaller N. So I'm just going to write that down. Sorry, give myself some more room. Not my best grammar, but if you reflect off a larger index of refraction, you get a different outcome than if you reflect off a smaller N. We'll need that when we start putting all of this thin film stuff together. I'm going to talk about the third point in this video as well, and then we'll put it all together and we'll actually talk about thin films. The third one is, hopefully after what we've done with the single slits and the double slits and the gratings, interference is all about the difference in distance that waves travel, and it's a comparison of the phase of one wave compared to another. If we have two waves that are in phase with each other, crests and crests, troughs lining up with troughs, we call that constructive interference, and we get a bigger wave. In terms of light, bigger wave means bigger amplitude. In terms of light, that means brighter. The opposite is destructive interference. If we've got crests lining up with troughs, troughs lining up with crests, then we're going to call that destructive interference, and the waves cancel each other out. If they're a perfect match, they would perfectly cancel each other out and we wouldn't have any wave. In terms of light, a much, much smaller amplitude or just a smaller amplitude means less bright. So we're going to put it all together next. But remember that this is an interference topic, thin film interference. It's going to be a comparison of the phase of one wave to another wave. It'll just be they've gone through different things, potentially different reflections and traveled different distances.